All right, so let's see, 2.5, motion with constant acceleration. So yesterday we talked about acceleration, introduced it. This time we're gonna be doing some problems. We have some formulas to talk about, and then we're gonna get going. So velocity along any axis, so the x-axis, y-axis, whatever, for an object with a constant acceleration is given here. We have, so velocity along the x direction, final, equals velocity in the x direction initial plus the acceleration times delta t. So this is the acceleration in the x direction. So notice everything is in the x direction here. This is going to work along the y-axis as well. So if I'm going in the y direction, then all of these x subscripts would just change to y subscripts, okay? This is important for us when we're moving in two dimensions. So if I'm moving in two dimensions, then I will have, as you will see, we'll break the motion into parts where we have an x direction part and a y direction part. Those parts are called components, which we'll get into. But for now, we're just moving in one dimension. So that's what we're worried about. So for right now, because of that, we can simplify this to just v sub f equals v sub I, not equals, plus a delta t. If we're just in one dimension, then we don't care so much about the x subscript because we know we're just in one dimension anyway, so it doesn't really matter. The position equation for an object with a constant acceleration. So if I'm moving in the x direction, then my position would be in terms of x. So x sub f equals x sub I, x final equals x initial, position final equals position initial, plus, and then v sub x, velocity in the x direction initial, delta t, plus 1/2 times the acceleration in the x direction, delta t squared. And all of these subscripts are there to help us when we're dealing with motion in two dimensions. So that's why they're being listed here. But like I said, when we're dealing with just one dimension, we can simplify the equation and we don't need to deal with those subscripts as much. We can get rid of the v sub x, that x subscript there, and the a sub x, that x subscript. We can get rid of those and we don't have as much of this notation to write, which is kind of nice. But beware, because when we deal with two-dimension stuff, we need those subscripts, okay? So that would simplify to this, x sub f equals x sub I, and then we have plus velocity initial delta t plus 1/2 acceleration, and then this delta t is squared. So we just got rid of the sub x, that subscript there. And really it didn't simplify anything, it just let us not write quite as much, which is nice. And then we have an equation that relates velocity and displacement for a constant acceleration situation. And that is important to note. This is all constant acceleration. If we don't have constant acceleration, then these equations don't work. So if I want to relate velocity and displacement in a constant acceleration situation, then I have v sub x final squared equals v sub x initial squared plus 2 times the acceleration in the x direction, delta x. This is all in the x direction. If it was in the y direction, then all of the x's turn into y's, and it's the exact same equation, okay? And if I'm just dealing with one-dimensional motion, then once again, I can get rid of that x subscript, and I wind up with v final squared equals v initial squared plus 2 acceleration delta x. And again, it's the same exact equation. We just don't care that it's the subscripts because it's one-dimensional motion, and what difference does it make then, okay? And again, if it was in the y direction, then this delta x would turn into delta y. Okay? So these formulas are very important formulas. We're going to be using them and manipulating them constantly. And there are problems where we'll need to work with one formula to get enough information to work with the other formula that will give us the answer that we're looking for. Okay, so we use them interchangeably all the time. And also we'll work with multiple equations at the same time. So,
Those are complex equations.
they're actually not complex equations. So,
They look complex.
they look complex because of all the letters and stuff, right? But they're actually not. So if you remember one of the formulas that we were looking at before, like acceleration is your rate of change, and velocity final is just like your y equals. Velocity initial is like your y-intercept of your linear equation. So that's just your b. And then a is your rate of change. That's your slope. And delta t is how long you're letting it go for, and that's your x. It's really just slope-intercept form, okay? That's exactly what we're dealing with here. But in physics, we want each of these letters to represent exactly what it is that we're looking at. So that's why all of those letters are different than what you saw in Algebra 1. But really all we're doing is we're working with Algebra 1 or Algebra 2 equations. Okay? On this one, we see a delta t squared, and we see a delta t, right? We also see an x sub final. So this is a position equation. That's why it's x and not v. But that's still going to be x sub final now is y equals x initial is the y-intercept of the equation. Okay, so that's the constant that we would see in the equation. We have a delta t squared. That's acting like our x. There's some number attached to it. Okay, so that's like a x squared plus bx plus c. This is an Algebra 2 standard form equation for a parabola.
Oh, what?
Okay? It's nothing new. You did this equation in Algebra 2. You did this equation in Algebra 1. So we got Algebra 1, Algebra 2 going on here. Okay? But the letters are different to represent what's actually going on physically in the real world. That's all. Okay? If you think of it that way, it's not really that big of a deal, right? Okay. And the third one is similar, except this time we have velocity final, but it's being squared. So this is actually a square root equation. If I were to square root both sides, I'd have velocity final by itself, which you also dealt with in Algebra 1. Or sorry, not Algebra 1, Algebra 2. That was an Algebra 2 situation. Okay, so enough of that. So now for uniform motion, and remember what uniform motion is? What is it?
Constant speed.
Constant speed. So let's write that up here. Constant speed. It never hurts to remember what that means. So if we have constant speed, what is the acceleration?
Increasing.
Constant speed. What is the acceleration? 0, that's right. Okay, so then what's the velocity?
Consistent? I don't know.
Constant, yeah. Okay, so then how does the position change if the speed is constant?
Time.
How does position change?
Isn't it like by that set, like the meters per second per second? Or-
No. We're talking about position now. Meters per second is acceleration.
Wow.
But they could also, it depends on the,
Position. How does your position change if your velocity is constant?
The change is constant?
The change is constant, so the position changes steadily.
instead,
Kind of a tricky question there. Maybe the word didn't come to mind, but your position is changing steadily, okay? Now, for motion with a constant acceleration, okay? So is our speed constant here?
no.
No, it's not going to be constant. Is our acceleration constant?
Yes.
Yes. So acceleration is constant. Is the velocity constant?
No, it's increasing.
No. Is it steadily changing though?
Yes.
Yeah, we saw that last time with the velocity versus time graph when we had a constant acceleration. It is steadily changing. the graph looks like a line. Okay? So how does position change then? That's the real question. And actually, if you were paying attention like a minute ago, maybe not more a minute, but here is your position equation right here for a constant acceleration. What does that graph look like? Looks like a parabola, that's right. So how does motion with a constant acceleration look for the position?
Parabola.
Looks like a parabola. So what we're gonna write though is not a parabola, because that's not how we would see it physically as we were like driving down the road. It's not like we're looking at parabolas all the time, right? It changes as the square of the time interval. So that's expressed mathematically, right? So it changes, the position changes as the square of the time interval. So 1 second goes by, the position is going to be changing now as the square of the time interval. And if I graphed it, then that's where the parabola starts to show up.
When we do our lab on Monday.
Maybe.
Okay.
All right, you're driving your car at 15 meters per second, and remember that our easy conversion for that, if we double the meters per second and then add a little bit, we get a good approximation for miles per hour. So double 15 meters per second, you'd have 30. Add a little bit, we're going to be around 35 miles per hour. Okay, makes sense? So we're driving through the neighborhood. 35 miles per hour is pretty fast in the neighborhood. So don't do that. When a child runs out in front of you, we're going way too fast for that situation. You hit the brakes and stop as quickly as you can. Your vehicle comes to rest in 1.5 seconds. How far does your vehicle travel as you brake to a stop?
It's crazy.
You've stopped in 1.5 seconds, right? The kid runs out in front of you, but you're going about 35 miles an hour in the neighborhood. How far did you go in that amount of time? What do?
We slow down.
The first thing we do is we write down everything that we know, okay? So what do we know?
We're going 15 meters per second.
We're going 15 meters per second to start. That is V sub I. So we write that down. V sub I is 15 meters per second. Okay, if we know V sub I, then what's V sub F?
0.
That's right, we came to a stop. So V sub F equals 0 meters per second. And when you do this, write down the units as well. Okay, now, we also know that we came to a rest in 1.5 seconds. What is that?
B sub F. I mean T sub F.
That's actually delta T.
Oh.
Time to start was 0, time to finish was 1.5 seconds. If we subtract the 2, we get delta T. So we'll just go straight to delta T. Delta T is 1.5 seconds. Okay, now those are the things that we know. They gave us all of those numbers essentially, right? What is it we're looking for?
It's not beautiful.
Good.
Thinking's over.
What is the question asking us?
What's the deceleration?
No. Look at the question. What is it asking us?
How far does your child do?
How far do you go? What is that?
Distance. Position.
That is your distance traveled. And what letter is that?
V, no.
A.
No, that's acceleration.
Delta,
Delta X.
Delta X, you got it. So we are looking for delta X. How far did we go? Okay? You write down what you know and what you don't know. Okay, now along the way, we might need to calculate something that we also don't know. We don't know how our acceleration was behaving, okay? We don't know anything about our acceleration either, so we write that down. If we knew our acceleration, we would easily be able to use one of our formulas that would tell us our delta x, okay? Because the formula that tells us delta x involves acceleration, all right? So how could I calculate acceleration in order to use that formula that would allow me to calculate my delta x?
15 meters per second over 1.5 seconds.
So you're using this formula. Acceleration equals delta v over delta t. So we write that formula down. We already know
So 2.
delta t. How do I calculate delta v?
Subtraction.
Yes. So delta V is V sub final minus V sub initial over delta T. It's important that you write that down because you might screw it up and just call it 15 meters per second, but it's not actually. It's 0 meters per second minus 15 meters per second divided by the delta T, which is 1.5 seconds. Remember, delta T is always positive. And what do we get?
Negative 15 meters per second over 1.5 seconds.
Okay.
That's just
What is this?
negative 10 meters per second.
It is negative 10 meters per second. But it's not meters per second.
Per second squared?
It's meters per second squared. Remember, acceleration is meters per second squared. And on top, we have meters per second divided by another seconds. So that's going to make meters per second squared. Okay. Now, we're not looking for acceleration, but we needed acceleration to be able to use another formula. Which formula are we talking about here?
The parabola one.
Well, we could. Let me go back. And I got to go through this one too. Okay. So we have all of these formulas that we could use. We want delta x, right? So this top one right here does not have delta x in it. This one right here does have delta x if we slide x sub I over.
So the third one.
The third one, so this top one does, or this one right here does have delta x in it. If we move x sub I over, we'd have x sub f minus x sub I, which is delta x. So we could use this one. This one down here at the bottom also has delta x in it. Do we have v sub f?
Yes.
Do we have v sub I?
Yes.
Do we have the acceleration?
Yes.
So we probably would just use that one, okay? So I'm sliding back here. Tell me what that equation is.
V sub f squared equals v sub I squared plus 2 acceleration delta x.
Okay, now what do we know?
The v sub f, v sub I.
V sub f is,
15. Oh, no, 0.
v sub f is 0. So this term right here turns into 0. Notice how I mark that. Okay, now, before you plug in numbers, solve for the variable that you're looking for, okay? Get in the habit of doing this. Don't plug in numbers first.
So negative vi
So we're going to subtract v sub I squared from both sides.
and subtract 2a.
No,
No?
we're not subtracting. That is all multiplication
Oh, that's
here.
all 1? Okay.
2 times a times delta
So
x.
divide by 2a.
So we're going to divide both sides by 2a. So divide both sides by 2a right here. And now I have equals delta x by itself. Okay?
Now
We're going to do that every time. Solve for the variable before you plug anything in, okay? You got to trust me on that. It is way easier now. Okay, so we have negative, and then in parentheses, the v sub I is 15 meters per second, and it's being squared.
over
2 times
negative 10.
the negative 10 meters per second squared.
Squared.
That's not being squared. It's just meters per second squared, right? That's the unit for acceleration. Now, sitting here, I don't want to just jump on my calculator. I want to try to simplify this. I notice that I have a negative on top and a negative on the bottom.
So negative 1.
So negative divided by negative turns positive, so I don't have to worry about the negative sign anymore. I have
5s.
15 being squared. Do I know what that is? If you don't know what it is, no problem. I have 2 times 10, which is 20. So now if I go to my calculator, I don't have to type as much. I have 15 being squared, divide by 20 instead of 2 times 10, right? So 15 squared is 225. Okay, now I could divide by 10 and move the decimal over 1, 22.5, and then multiply by 2, 44, and 1, 45, right?
Yeah.
Okay, so I have 45.
45.
What are the units?
Meters per second.
But the meters can
Meters goes away.
meters goes away. One of the s's can go away. So it just
No,
be
because
45
meters went squared.
seconds.
Meters went squared, so it's still
So it's just
meters squared s squared. So it's just meters.
meters per second.
That's right. Meters squared on the top divided by meters on the bottom leaves me with meters.
So it's just
per second squared on top, per second squared on the bottom, those are gone. So I'm just left with meters. Now, the big question is this the right answer?
I don't know.
I don't know
How far
either.
does your, yeah, because it says, how far does your vehicle travel as you brake to stop?
I
So it's
don't
asking
think
the
so.
distance that you traveled while you were braking.
Is
So
it
that's-
4.5?
We did make a mistake. Where is it?
4.5?
The decimal.
No, we're not multiplying by 2 on the 22.5, we're dividing by 2. This is divided by
Oh.
2. So,
Divided by 10 times.
So it's 225 divided by 10, which is
45 divided by 4, which
No, because it's
11.25.
225 divided by.
there you go, 11.25. Significant figures would take us to what?
11.
So 11 meters. Now, definitely better than 45, right?
Yeah.
11 meters, though, is still like 35 feet.
That's a lot.
Kid runs out in front of your car,
It's getting hit.
you're gonna hit him.
Uh-huh.
And that's why the neighborhood speed limits are not 35 miles an hour.
It does not take you 35 feet.
It does.
If you go,
You're going 35 miles an hour. It takes you a while to stop. Plus, you got reaction time. So,
Yeah, even
there you go.
worse.
That's how you do those problems.
but like, have you seen the thing? Well, I'm guessing you've
You're
seen
gonna
it
have to
before,
trust.
Where it's like, all right, you have this high of a percent of a chance to be on.
Now, motion under constant acceleration, the formulas are showing us that position changes as the square of the time interval. If the velocity to start with is 0, then the position equation simplifies to this. This is only if the initial velocity is 0. If you're gonna remember a formula though, remember the original formula, not the special case. So this is x sub f minus x sub I equals, remember that's delta x. So we would have this formula right here with initial velocity being 0. It's a quadratic relationship. We see that the variable here, the delta t, is being squared. That makes a quadratic relationship. I graphed it, I see a parabola. The dependent variable is proportional to the square of the independent variable. The dependent variable here is delta x. The independent variable is delta t. So we square delta t, we get delta x. Y is proportional to the square of x in this equation. This is the algebra version of what we're looking at right here. So the graph of a quadratic relationship is parabolic. We see a parabola. That's what we've been saying. If you increase x by a factor of 2, you increase y by a factor of 2 squared. So if you know the shortcut when you're graphing a parabola, that's exactly what this says. I go over 1, I go up 1. I go over 2, I go up 4. I go over 3, I go up 9, right, when I'm shortcutting the graph of a parabola. If you decrease x by a factor of 3, then you decrease y by a factor of 3 squared.
Same thing.
Same idea, we're just going the other way, right? So generally, changing x by a factor of c changes y by a factor of c squared. That's the idea, okay? I've just said the same thing like 3 different ways. We good?
Yeah.
Okay.
You're gonna make me have another bloody nose.
Yeah, yeah. Try not to have a bloody nose over it. It's not that big of a deal. Okay, so a drag racer starts from rest and travels 6 meters in 1 second. What's the independent variable here?
6 meters.
No,
No.
time.
Oh, 5 seconds.
Time. So suppose the car continues this acceleration for an additional 4 seconds. An additional 4 seconds. How far from the starting line will the car be? What do you think?
6 meters per second per second. So 6,
6 times
then
4.
12, then 18, then 24.
I just said 24 meters from the starting line.
No, it's not 24.
That'd be 30. More than 30 because of the acceleration.
It's more than 30.
Yeah.
So we started from rest, right? We're in a quadratic relationship because we have an acceleration. We went 6 meters in 1 second.
So the equation be 6 meters per second squared.
So the acceleration is
6 meters.
Second squared.
the delta V over delta T, 6 over 1, okay. So now what? We can write that down, acceleration equals delta V over delta T, 6 meters per second over 1 second, 6 meters per second squared. Okay, so we know the acceleration, which we could do in our head, that's fine. Wanted to write it down though. Now what?
Plug it into that final one. Wait. How far from, we want delta x.
We want delta x, yep.
We want the start and the ending point. That one?
So delta x is x sub f minus x sub I, yeah. But x sub I was 0 if we make the origin where it started, right? So x sub f really is what we're looking for, but we can call it delta x because x sub I was 0.
Oh, okay.
So delta x equals,
This is probably wrong.
what?
90 meters.
No.
Yeah, it's wrong.
V
What is the delta t here?
delta t is 4.
No.
Time? Seconds?
It's an additional 4 seconds. So what is the delta t?
5 seconds.
It's 5 seconds.
Because they've
Okay.
already traveled 1 second.
Right.
They're traveling an additional.
The 1 second gave us the acceleration, but the total time now is 5 seconds, okay? So the delta t is 5 seconds under the same acceleration. So reason through it.
30 seconds. Or
5
thir-
seconds.
30 meters, sorry.
No, we definitely go farther than 30 meters.
Because it goes
Why?
up.
Because if it's 6 meters, oh, wait, no, 6. So
This is a
it's-
parabolic relationship.
6, 12, 18, 24, 30.
So it'd be a square root of 6 to the power of
That'd be-
4. Which is 72?
No, but you're close. The formula I just gave you guys
Okay.
was when the initial velocity is 0,
Yes.
1/2 a delta t squared.
We don't know what A is.
Yeah, we do. We just calculated it.
Oh, 6.
Yeah.
6 meters.
And time was 5 seconds. So
That's
delta
30.
t squared is,
So it's 30 squared is 90.
no,
5.
Or it's
5 squared is,
25.
okay, our acceleration is 6. And then half of that is,
25
Three.
times.
so
So it's 75 meters.
1/2 times our acceleration, 6 meters per second squared, times delta t, which is 5 seconds being squared.
That's 25, 6 times 20. Oh, and half times, so it's 25, so it's 75
75 what?
meters.
Meters.
That's 15 meters off.
15 meters off is kind of a big deal.
That's quite the distance.
All right, so ideally we're using, let me go back to this real quick. We're using this concept, generally changing the independent variable by a factor of c changes the dependent variable by a factor of c squared. If I go back to this, we changed the independent variable time by a factor of, it was 1, now it's 5. We changed the independent variable by a factor of 5. I needed to square that, get 25. And all I'm doing now is I'm taking that 25 and multiplying it by the front of that term, okay? I would like to do that without having to write anything down, because then I'm going to be a lot faster, okay? The concept here is it's a parabolic relationship. It's just like in Algebra 2 when you got good at graphing parabolas and you were just going over 1 up 1, over 2 up 4, over 3 up 9, okay? Understanding that concept is nice. It's not essential, but it's nice. Okay, a cyclist is resting at a traffic light. When the light turns green, he begins accelerating at 1.2 meters per second squared. How many seconds after the light turns green does he reach his cruising speed of 6 meters per second? What do we do?
we know.
What do we know?
A.
We know his acceleration.
No, is it?
Okay, yep, they told us acceleration. What else do we know?
The end.
What's the end?
6 meters per second.
What is that?
VF.
VF. Okay, what else do we know?
He starts from a rest.
Okay, so what's that?
So V equals
VI,
is 0.
meters per second. Anything else?
I don't believe so.
What are we looking for?
We were looking to see how many seconds after the light, how long it takes him to get from 0
Right,
to 6.
Right. So what is that we're looking for?
Time.
Time. Delta T then. We don't know. Okay. What can we do?
Find delta x. No.
Do that one we just did, the 1/2 A. Oh, and then yeah, then just flip it to the other side, and then we get delta T squared.
Okay. If we have acceleration, we know V sub F and V sub I, which means we actually know delta V, right?
Yeah.
We have acceleration, we have delta V, and we are looking for delta T. Is there a formula that involves all three of those things?
Mm-hmm.
What is the formula?
That one.
What's that
We
one?
have VF. Okay. So we have VF equals VI plus a delta T. So you could just subtract the VI and then divide it by the A.
You're going way more complex than you need to.
Can we just do that one?
What is it? What is that one?
The 1/2 A parentheses delta T squared.
That's even more complex than it needs to be.
This one, the very first one.
What's that one?
V sub F equals V sub I plus acceleration times delta T.
That's what I just said.
I don't know.
I said then you just
That's even more complex than it needs to be.
then you just move them. You just
Which
move
one?
two of the factors over.
How about this? Acceleration equals delta V over delta T.
Oh,
That okay.
that's very simple.
That's what we have, right?
Yeah.
We know acceleration and we know delta V, and we're looking for delta T. So how about that one? Okay, so I want to solve for delta T though before I do anything. So I multiply both sides by delta T, and I divide both sides by A. I have delta T equals delta V over A.
And which is 6 meters a second over 1.2 meters a second squared.
Okay, I just got to know what 6 divided by 1.2 is.
5
5, what?
meters. Or it'd be seconds.
It would be
5
seconds. The meters divide out here, and then seconds per second divided by per second, that part would be gone. And I'm just left with on the bottom of per second, which flips and becomes seconds on the top.
Which is delta T.
So 5 seconds is your answer.
It takes them 5 seconds
had
to go from 1.2 meter, or to go from 0 to 6.
Yeah. You're on a bicycle. It's going to take you a minute. You're accelerating at 1.2 meters per second squared. Okay? So, lesson to learn on this problem is look at what you have and what you're looking for, and don't overcomplicate it with some massive formula. Use what is simple, if possible, right?
I feel like it was just as much. I feel like that was just as much work.
Maybe it was, and maybe the formula that you used would have gotten you there, and it would have. But you have these simple ones here, use them. Okay, so that is it, we're done.